So hello everyone, so in this lecture video we are going to be talking about intermolecular forces and the states of matter. And when we're talking about states of matter, we're actually talking about the three common ones: solid, liquid, gas. Just as an FYI, there's actually a fourth state of matter called plasma. Okay, we're not going to be covering that this semester. In this diagram, okay, in this actual image, we can see that solids here, if you look at the continuum for IMF, has the highest intermolecular forces, and gases do not actually have the least intermolecular force. However, highest kinetic energy. And you have to understand that the phases of matter, and we're talking about phases of matter at room temperature at this point, is based upon the forces of attraction between adjacent atoms or adjacent molecules or adjacent formula units. Okay, so this is again, and folks, this comes from intermolecular forces, and intermolecular forces in turn comes from the type of compounds that are actually present. Okay, so one of the intermolecular forces that's actually present between all atoms, I don't care which atom, whether you're like a single atom, whether you're like a covalent molecule, whether you're like a formula unit ion, okay, this is present among all particles. Okay, so what happens, folks, is if you are an atom, just a lone atom zipping by yourself, what happens is, generally speaking, you're neutral. Okay, you have your nucleus, which is positive in the middle, and you have your electrons and like on the periphery and the orbitals. But once in a while, what happens is, because of some forces of nature, like we're not going to talk about that, what happens is it is also possible at any moment given time, and it's going to be very, very brief. What happens is the actual orbital gets warped, in which all the electrons goes onto one side of the actual atom, and the nucleus then goes on the other side. Guess what charge is the nucleus? Positive. What's the charge of electrons? Negative. This is what happens for what we call dispersion forces, which is the weakest intermolecular force present between all molecules. Okay, and this is momentary, it's very brief, and it's not very, very strong. Okay, here we have another example of intermolecular force. So this is called ion-ion interaction, and the reason why it's called ion-ion interaction is it's interaction between two ionic, in this case, particles. So you have, if you guys can see this, the green blobs are chloride ions, and the purple blobs are sodium ions. If you can see them, what happens, folks, is if you put adjacent sodium and chloride atoms, or in this case ions, next to each other, guess who's attracted to this positive atom? Something negative. Well, who's negative on the other atom, on the other compound? Well, chlorine. And guess who's attracted to this one? Sodium. And then that's actually why you actually have this structure, right? So you actually have this lattice structure in which you have, in this case, repeating structures in which sodium is attracting multiple chloride ions to itself, and then chloride atoms, like ions, is actually attracting multiple sodium atoms. So, and because the electrostatic or Coulombic forces are so strong, right, they pull on each other so tight that you actually see them at room temperature, and that's actually where you get salt crystals. Okay, that's the salt that you use to salt your eggs in the morning. On the right here is water molecules. Okay, the red blob is oxygen, the gray spheres are hydrogen centers, and again, note that hydrogen is partial positive and oxygen is partial negative. And folks, when you put water molecules next to each other, because all of them have a positive and negative poles, they will attract each other eventually, right? So there's also repulsion, by the way, just to give you an FYI, but this positive, partial positive end is going to be attracted to a partial negative end, and so on and so forth. And because of this attraction, they actually then interact with each other. Now, having said that, this is a partial positive charge. This is a full charges. So therefore, the interaction between water molecules is weaker than the interaction between two ions, okay? And so this is why water, like in this case, hydrogen bonding between water molecules, this is why this is liquid at room temperature, okay? Let's take for an example oxygen gas, right? Oxygen gas looks like this. Folks, this is a nonpolar compound. Nonpolar compound has no positive or negative, so therefore if I plug an oxygen molecule next to it, will it be attracted to something? Absolutely not. And that's why the only force present between nonpolar molecules is actually dispersion forces, okay? So again, the stronger the interaction in the individual compounds, the stronger the interaction actually in the aggregate in this case, or groups of those compounds, okay? This is an example of two ions, ions. This is an example of two polar molecules, all right? And hydrogen bonding, FYI, just like as an aside, is actually hydrogen connected to either oxygen, like water. It can also be connected to fluorine, or it can also be connected to nitrogen. So anytime you see hydrogen attached to any of those three molecules, you make an assumption that there's going to be hydrogen bonding present, okay? Now we're going to be moving on to solids here. So what we have not covered are metallic compounds, okay? So this is actually how a metallic compound looks in a structure if you do a close-up. So this positively charged centers here are actually the nucleus, okay, of, let's say for instance this is copper, okay, copper atoms, the copper 2+ form, okay. So what's gonna happen is, I don't know if you know, please recall that metals hate, in order for them to like meet octet rule, they wish to get rid of their electrons, okay. Having said that, if you are a metal adjacent to another metal, all of you want to get rid of your electrons, right? No one wants to get an electron. So the way that metals actually do this is they actually do something similar to covalent bonding. So what happens is, in fact, I'm going to simplify this now because copper is a little bit simple now. Let's just look at sodium in this case, which has one electron on its valence shell. What actually happens, folks, is in order for it to be filled, it's gonna bond, similar to covalent bonding, with 7, or actually in this case, 7 other sodium atoms. And so therefore, it will have a full octet. Okay, this is an oversimplification, but it's gonna meet the needs of this class. So what happens, folks, remember now, so what happens is you're going to have multiple sodium sharing multiple electrons. So because of that, those electrons just basically move all over the place. So they're what we call delocalized, meaning to say do not stay in place. This is one of the reasons why metals conduct electricity. Conducting electricity means to say that if I give you a 10-foot piece of, in this case, iron, if you touch one end and I put an electric, in this case, current on one end, you're going to feel the current, okay? And the reason why you feel the electric current is when you apply an electric current, it's actually the electrons are actually moving around very rapidly on the surface, okay? So this is actually a solid. And again, the reason why it's a solid at room temperature, it has bonding similar to covalent compounds. The only difference is in covalent compounds, the electrons that remains in place, they are localized. In metallic bonding, those electrons are delocalized. Okay, and then we have other things. We actually have covalent solids as well. Okay, and you probably are aware of very expensive covalent solid. It's called diamond. Okay, FYI, folks, the structure of diamonds and the lead or graphite in your pencil is actually the same. The only difference is in graphite structure, the actual bonds, the covalent bonds, is actually linear. So they are actually, in this case, pleated in lines. Whereas if you look at the diamond structure, they're actually connected three-dimensionally. It's not connected just two-dimensional. It's also connected three-dimensional. just as some news for you, the way that they actually create, in this case, lab-grown diamonds now, is they actually take carbon compounds that has a high amount of carbon, and what they do is they just compress it. Okay, and so compression then gives you this diamond, and then if you add some minerals, you actually get color. So two main types of solid in this case. There's also molecular solids, like ice is a molecular solid, but that's kind of more of a product of temperature. Okay, so we're not gonna talk about that too much. Ion solids, covalent solids. Okay, so I talked about before about intermolecular force as a big driver of what the state of matter is at room temperature. Folks, so in this case, we actually have, in this case, stearic acid, which is the actual fat that you actually see in a piece of meat. And then we actually have this thing called oleic acid, which is actually what you can see in vegetable oil. This is solid room temperature, and folks, this is actually liquid at room temperature. They're both 18 carbons. Okay, the only difference between them, folks, is the presence of a double bond. So if you look at this structure here, there's a double bond in oleic acid. Okay, and if you assume that stearic acid, there's multiple stearic acids, if you're linear like so, what happens is they can stack on top of each other. And if they can stack on top of each other, they can actually create a solid. Okay, so there's actually compression there. What happens, folks, is if you have a kink, like in a double bond, it's very difficult for you to stack on top of each other, and this is why oleic acid, which is a double bond as opposed to stearic acid, is actually liquid at room temperature. So structure, okay, also makes a big difference in your physical state at room temperature. Okay, and the number of atoms also makes a big difference as well. All right, so that's a very, very important concept to involve. This is a summary of intermolecular forces. Again, ion dipole. Ion dipole basically just tells you it's between an ion and a polar compound. Hydrogen bond, again, is any hydrogen attached to oxygen, fluorine, or nitrogen. Dipole, folks, just remember, it's just, again, two polar compounds. Ion-induced dipole. Ion means an ion. Induced dipole means polar. Polar, okay, non-polar. And then dispersion forces, which is the weakest, and the weakest bond in this case, intermolecular force, is actually between two non-polar molecules. Okay. Having said that, the states of matter is dependent upon two extrinsic properties, and that's the extrinsic, like in this case, external and like a condition, and it's pressure and temperature. Okay. So the big thing about, in this case, about gases, folks, is gases have large spaces. So if oxygen gas have large spaces between molecules. Okay. However, what happens is if you compress means you make them get closer to each other eventually, and that's a product of pressure. Eventually those two oxygen molecules is gonna be forced to interact with each other. Okay. And guess what happens when they get very, very close to each other? Well, if they were far apart before as a gas and now they get closer together, guess what? Now they have turned into a liquid. If I keep compressing them further, there's actually a point in pressure in which any gas can actually turn into a liquid, and it actually can turn into a solid, as you guys can see here. The transition between gas into liquid is called condensation. And the transition between liquid and into solid is actually called freezing. We've done that before, right? It's the same thing with temperature. What happens is kinetic energy is a product of temperature. So in this case, if you have a high temperature, the electrons, the atoms are going to be moving rapidly around. But if you cool them low enough into absolute zero, those atoms or those molecules will no longer move around. And so they aggregate as a solid as well. So there are two, again, in this case, external factors that actually affect the states of matter. And again, if you have a high enough pressure and low enough temperature, any gas can actually become a solid. Okay. And if you decrease the pressure enough and you increase the temperature high enough, any solid can actually become a gas. Please make sure that you're aware of all these terms of actually how you become a solid into gas. Okay. Sublimation and gas into solid, which is called deposition. Okay.